Good morning, dear students. Today we will discuss about the oscillators of the analog electronics subject. So, what is the oscillators and what is the application, advantage, disadvantage, and also we will discuss about the working principle of oscillators. So, an oscillator is an electronic systems. It comprises active and passive circuits, elements, and sinusoidal produce repetitive waveform at the output without the application of direct external input signal to the circuit. So, in oscillator, there is no direct external input signal to the circuit, and there are some active and passive components in the circuit of oscillators. So oscillator converts the DC power from the source to AC power in the load. A rectifier circuit convert AC to DC power. What an oscillator convert DC noise signals powers to its AC equivalents. The general form of a harmonic oscillators is an electronic amplifier with the output attached to the narrowband electronic filters and the output of the filters attached to the input of the amplifiers. So in this chapter we will discuss about the oscillator analysis is done in two methods. First, by a general analysis. Consider all other circuits are the special form of a common generalized circuit, and second, using the individual circuit by Kirchhoff law, Kirchhoff voltage law analysis, KVL analysis. So this is the introduction of the oscillators. And what is the difference between an amplifier and an oscillators? So here in this block diagram, show the difference between an amplifier and an oscillators. So in amplifier, basically input applied to the amplifier and a biasing supply also applied to the amplifier, and we can measure the output at the output terminal of the amplifier. What in oscillators, there is no input signals in this oscillators, and we also only a biasing supply to the oscillators, and we find out the output and can we measure the output with the output terminal of the this oscillator. So in this oscillator there is no input signal applied. Next one, classifications of oscillators. So oscillators are classified based on the type of the output waveforms. If the generated waveform is sinusoidal or close to sinusoidal with a certain frequency, then the oscillator is said to be a sinusoidal oscillators. And if the output waveform is non-sinusoidal, which refer to square or sawtooth waveform, the oscillator is said to be a relaxation oscillator. So basically, uh, there are two type classifications of oscillator. One is sinusoidal oscillators, and second one is the non-sinusoidal or relaxation oscillators. And an oscillator have a positive feedback with the loop gain have the infinite. Feedback type sinusoidal oscillators can be classified as LC inductor capacitor and RC resistor capacitor oscillators. So upon the feedback, there is the two types oscillators. that is classified in LC and RC oscillators feedback. The classification of various oscillators is shown in this table. So different type of oscillators and their frequency range. So types of oscillators. So first type of oscillator is audio frequency oscillator, which have the frequency range U 20 Hz to 20 kHz. Second one type of oscillator is radio frequency oscillator, which have the frequency range U 20 kHz to 30 megahertz. Third one is the very high frequency oscillator, which have the frequency range 30 megahertz to 300 megahertz. And next one is the ultra high frequency oscillator, which have the frequency range 300 megahertz to 3 gigahertz. And next one is microwave oscillators, which have the very high frequency and they have the frequency range from 3 gigahertz to 30 gigahertz. And next one is the millimeter wave oscillators, which have the frequency range 30 gigahertz to 300 gigahertz. So these are the different type oscillators and their frequency ranges here given in these tables. So circuit analysis of a general oscillators. So here given a generalized oscillator circuit analysis. This section discusses the general oscillator circuit with a simple generalized analysis using the transistor as shown in this figure. An impedance Z1 is connected between the base band and emitter E here in this circuit diagram, and impedance Z2 is connected between the collector terminal C and emitter terminal E. So to apply a positive feedback, Z3 is connected between the collector and the base terminal. So this is given here in this diagram. So all the other different oscillators can be analyzed as a special case of the generalized analysis of oscillators. The above generalized circuit of an oscillator is considered using a simple transistor equivalent circuit models. The current voltage expression are expressed for this circuit. So V1 equal to H1 I1 plus HR V2 equal to HI I1, as the numerical value of HRV2 is negligible, so V1 equal to HI I1 and I2 equal to HF I1 plus H naught V2 equal to HF I1. As the numerical value of H naught V2 negligible in this equation can be written as I2 equal to HF I1. So apply KVL at loop first in the given figure by consider that current through the impedance Z1 is I1 minus I3. So we get V1 plus Z1 into I1 minus I3 equal to 0, or V1 equal to minus Z1 I1 minus I3 equal to Z1 into I3 minus I1, and substitute the value of voltage V1 from these equations. We have get H I1 plus Z1 I1 minus Z1 I3 equal to 0, and I1 into H1 plus Z1 equal to Zi I3. So apply KVL at loop 3 in this circuit diagram. The voltage across the impedance Z2 will be V2 plus Z2 into I3 plus I2 equal to 0. So substitute these value of current I2, we have get Z2 HF I1 plus Z2 I3 plus V2 equal to 0, and also applying the KVL at load 2 by consider voltage across Z3, we get uh, I3 Z3 plus I2 plus I3 into Z2 plus I3 minus I1 into Z1 equal to 0, or I3 Z3 equal to V2 minus V1. So substituting the value of V1, so we find that I3 Z3 equal to V2 minus HI I1, and I3 Z3 minus V2 plus HI I1 equal to 0, or V2 minus HI I1 minus Z3 I3 equal to 0. So this equation can be written as in three variable I1, V2, I3 using Krammer's rule, and from these equations we get the following matrix, and after solving these matrix we have the uh, following equation given here, and let Z1 equal to R1 plus Z, Jx1 equal to Jx1, uh, and Z2 equal to R2 plus Jx2 equal to Jx2, and Z3 equal to Jx3. By adding, we get Z1 plus Z2 plus Z3 equal to R plus Jx. So where R equal to R1 plus R2 plus R3 is not negligible in comparison with X equal to X1 plus X2 plus X3, as we shall see X equal to 0. We see X equal to 0 at frequency of oscillation. So we have these equations in the form of Z1, Z2, Z3, and also HF and HI, and equaling imaginary part equal to Zx1, Jx2 equal to minus x1, x2, and Jxhi equal to 0 and x1 equal to 0, and equating real parts also we have get the x1, x2, hf plus x1 into x2, h3 minus h I dot r equal to 0, and substitute the value of these we get the value of hf equal to x1 upon x2 plus r into hi upon x1, x2. So this is the general condition for oscillations for a oscillators. Different type of oscillator circuit with different configuration can be analyzed through this general method. So this makes the analysis simpler. So, so first type of oscillator is the Hartlay oscillators. Here given the circuit diagram of the Hartlay oscillators. In Hartlay oscillators contains two inductors, that is L1 and L2 as shown in figure here, and X1 and X2 are inductance and X3 is a capacitance. So here X1 equal to omega L1, X2 equal to omega L2, and X3 equal to minus 1 upon omega C. So substituting the values of these in the general equation of the oscillator and considering R is small. So we have HF equal to omega L 1 upon omega L2 plus R into HI omega square L1 L2. So substitute these value and we get the condition for oscillation considering R is small. So HF equal to L1 upon L2 and HF equal to L1 plus L2 plus R CHI upon L11, and where L11 equal to L1 L2 upon L1 plus L2. and also L11 into 1 upon omega square C equal to L1 L2. So we have L1 upon L2 plus RHI upon omega square L1 L2 equal to L1 upon L2 plus RHI upon omega square L1 L2 equal to L1 upon L2 plus RHIC upon L11. Next one is the Colpitts oscillators. So this is the circuit diagram given here of the Colpitts oscillators, in which two capacitance and one inductors are used in the feedback network. So capacitor C1 and C2 and inductor L1. In Colpitts oscillator contains two capacitors and one inductors, and X1 and X2 are capacitance, X3 is inductance. So Z1 and Z2 are capacitors, and C1 and C2 are capacitances, and Z3 is an inductor of inductance L. So X1 equal to minus 1 upon omega C1, X2 equal to minus 1 upon omega C2, and X3 equal to omega L. So X1 plus X2 plus X3 equal to 0, and we have the minus 1 upon omega C1 minus 1 upon omega C2 plus omega L equal to 0, and also 1 upon L into 1 upon C1 plus 1 upon C2 equal to omega square, and we have the value of omega equal to under root 1 upon L into 1 upon C1 plus 1 upon C2. So frequency of oscillation of this Colpitts oscillator 2 pi f equal to 1 upon under root LC, or f equal to 1 upon 2 pi under root LC. So this is the frequency of oscillation of the Colpitts oscillators, where 1 upon C equal to 1 upon C1 plus 1 upon C2. So HF equal to X1 plus X2 plus RHI upon X1 X2. Therefore, condition of oscillation HF equal to C2 upon C1 plus RHI omega square C1 C2, and C1 C2 plus RH omega square C1 C2. So R equal to resistance of the coil 2. So R equal to C2 upon C1 plus R HI upon 1 upon L into C1 plus C2 upon C1 into C2 into C1 C2. चूंकि because omega square equal to 1 upon L into 1 upon C1 plus C2. So where R is the equal to C2 upon C1, neglecting RHI upon L into C1 plus C2. Next type oscillator is the phase shift oscillators. So this circuit diagram, so the phase shift oscillator equivalent circuit using the approximate equivalent circuit of the transistors. So the circuit diagram of the phase shift oscillator with 3 pairs of RC combination, and this equivalent circuit presentation of phase shift oscillator as shown in figure. By applying KVL in the circuit, we have the mesh ABCHU at loop 2. So we have these three equations, and next at mesh CDGH at loop 3 we have also two equations, and at mesh CDEFGH at loop 4 we have these equations. So eliminating I1, I2, I3 order wise, so we can write in this equation in the form of matrix. And this is the equivalent circuit representation of a phase shift oscillators. Dividing each element of the determinant by R. So let Xc equal to Xc upon R equal to A. So put the value of Xc upon R equal to A and we find this determinant, and solving this determinant and equating the imaginary part, and we have j into minus a squared 2a plus 12a equal to 0. So we have the a equal to under root 10. So we have xc upon r equal to under root 10 and xc x square upon r square equal to 10 and 1 upon omega square c square r square equal to 10, and also omega square equal to 1 upon 10 c square r square. So we have the omega equal to under root 10, 1 upon under root 10 cr, and also equivalent circuit of a phase shift oscillator is given here. So Z1 is series combination of R1 and JX1, and Z2 is the parallel combination of R2 and JX2, and V1 equal to input voltage here. So frequency of this phase shift oscillation equal to F equal to 1 upon 2 pi under root 10 CR. So this is the frequency of the phase shift oscillators. Next, equating the real part of the equation of the determinant. So we have the 8 minus 6a square minus 4 plus HFE. So we have the value of HFE equal to 56. For sinusoidal oscillation, HFE of 56 for R equal to RL. The equivalent circuit diagram of phase shift oscillator is given our figures. So next type of oscillator is the Wien bridge oscillators, and this is the circuit diagram of Wien bridge oscillators. So first one is the Wien bridge oscillator, and second diagram show the Wien bridge oscillator with an amplifier. So Wien bridge oscillator is the series and parallel combination of resistance R and capacitance C according to War-Hussein criteria. War-Hussein criteria is that product of AB beta equal to 1. So since AB into beta equal to 1, so beta equal to 1 upon AB and equal to 1 upon VR upon V naught, and also AB equal to 1 upon beta equal to Z1 plus Z2 upon Z3, and also 1 plus Z1 upon Z2, where Z1 is the R plus JX1 series combination, and 1 upon Z2 is the 1 upon R2 plus 1 upon JX2 parallel combination. So A is the 1 plus R1 upon R2 plus X1 upon X2 plus JX1 upon R2 minus R1 upon X2. So this is the A. The two-stage RC coupled amplifier can be used by equating real and imaginary part. Considering only the real part, we have A equal to 1 plus R1 plus R2 plus X1 upon X2. This is the real parts of given equations. And second is the imaginary part, that is X1 upon X2 minus R1 upon X2 equal to 0. So X1 x2 equal to r1 r2 frequency of oscillation. So we have r1 r2 equal to 1 upon omega square c1 c square. So omega square equal to 1 upon c1 c2 into r1 r2, and if r1 equal to r2 equal to r and c1 equal to c2 equal to c, then a will be equal to 1 plus 1 plus 1 equal to 3, and omega square equal to 1 upon c square r square, or omega equal to 1 upon cr. So frequency of oscillation will be equal to f upon 1 upon 2 pi rc, and at the balance condition, the r3 upon r4 equal to r1 upon, sorry, z1 upon z2. This is the for oscillation conditions. So that is the diagram for the wheel bridge oscillators. From the circuit diagram of wheel bridge oscillator, we have R3 upon R4 equal to R1 plus 1 upon J omega C1 into 1 upon R2 plus J omega C2, and we write this equation in imaginary and real parts. So we have R1 upon R2 plus C2 upon C2 plus J omega C2 R1 minus 1 upon omega C1 R2. Equating imaginary parts, we have gate omega C2 R1 equal to 1 upon omega C1 R2, and omega square equal to 1 upon C2 R2, and because R1 equal to R2 equal to R and C1 equal to C2 equal to C, so we have R2 R3 equal to R1 upon R2 plus C2 upon C1. So R3 upon R4 equal to R upon R plus C upon C equal to 2. So what is the advantage of Wien bridge oscillator? So we have some advantage of the Wien bridge oscillators. First one is the frequency of oscillation can be easily vary just by changing RC network. And second advantage, high gain due to low stage amplifier. And third one is stability is high. So these are the some advantage of wheel bridge oscillator. But we have some also disadvantage of wheel bridge oscillators. So first disadvantage, the main disadvantage of the wheel bridge oscillator is that a high frequency of oscillation cannot be generated. So that is the main disadvantage of the wheel bridge oscillators. So next topic is the Nyquist criteria for oscillations. So Nyquist criteria states that if this closed curve passes through or enclose the point 1 plus j0, the amplifier becomes unstable and oscillates. So it is important to note that a positive feedback amplifier will not oscillate unless the Nyquist criteria is satisfied. So in this steady state condition, the open loop becomes unity and the oscillations are sustained. The frequency of oscillation is controlled by the frequency determining network of the oscillators. The RC and LC combination circuits are used in oscillators to serve as the frequency determining network. Let us summarize the key necessity of feedback oscillators. So first one is amplifier with positive feedback produce a negative resistance in the system. And second one, the frequency determining network creates oscillations at certain required frequency. And third one is the system non-linearity introduced by the devices contain the amplitude of oscillations. So in Nyquist criteria, here a figure given. In this figure, region of positive and negative feedback in the complex plane. So in this figure, X is a point on the locus AB, A beta. If X is inside the circle of unit radius 1 plus J 0, so we have 1 minus A beta is less than 1 and positive feedback occurs if X is outside the circle. So we have amplitude of 1 minus A beta greater than 1 and the feedback is negative in that case. And Nyquist criteria state that if this closed curve passes through or enclose the point 1 plus J 0, the amplifier becomes unstable and oscillates. It is important to note that a positive feedback amplifier will not oscillate unless the Nyquist criteria is satisfied. So this is the circuit diagram of the next type of oscillator is the tuned oscillators. So in this circuit A, a circuit diagram of tuned oscillator, and circuit diagram B is the AC equivalent circuit of this tuned oscillator circuit. So this circuit diagram of tuned oscillator, the emitter bypass capacitor CE shunt the AC so that emitter resistance is omitted from the AC equivalent circuit in second figure. So DC operating point of the transistor is determined by the resistance R1, R2 and emitter resistance RE and supply voltage. The transistor gives a phase shift of 180 degree. So circuit analysis of tuned oscillators. The frequency of oscillation is approximately given by the natural resonant frequency of the LC tank circuit. So thus we have F equal to 1 upon 2 pi under root LC. The resistance R of the transformer primary is small at resonance condition. So the resistance is RT of transformer equal to 1 upon L upon CR. So next one is the circuit analysis of tuned oscillators. From the H parameter AC equivalent circuit of given in diagram 2 or B, So we have V2 equal to minus I2 RT equal to minus I2L upon CR, and upon application of KCL at the point we have I2 equal to H naught C V2 plus HAP I1. Substituting V2 from given equation into this equation, so we have I2 equal to minus I2L upon CR HOE plus HAP I1, or HFE I1 equal to I2 into 1 plus HFE L upon RC. If M is the mutual inductance, then the voltage in the transformer secondary is J omega M IP into IP is the primary current. The secondary circuit impedance is RB plus HIE. Applying KVL in the secondary circuit, we obtain I1 equal to J omega N IP minus HREV2 upon RV plus HIE. And we have IP, and substituting IP and V2 values, and we have the equation 1 plus H naught E upon L upon CR equal to HFE upon RV plus HIE into omega square N plus HRE upon C into 1 upon LR, where omega equal to 1 upon under root LC. So we have M equal to RV upon HF into CR plus HOEL plus CR into HI upon HFE plus L into HIE H naught E minus HFE R HRE upon HFE. The value of M is used to calculate the condition for sustained oscillations. Now we will discuss about the next type of oscillator, that is the crystal oscillators. So what is the crystal oscillators? In crystal oscillators is most commonly used oscillator with high frequency stability. They are used for laboratory experiments, communication circuits, and biomedical instruments. They are usually fixed frequency oscillators where stability and accuracy are the primary considerations. In order to design a stable and accurate LC oscillator for the upper high frequency and higher frequencies, it is absolutely necessary to have a crystal control, hence the reason for crystal oscillators. Crystal oscillators are oscillators where the primary frequency determining elements is quartz crystal. Because of the characteristics of the quartz crystal, the crystal oscillator may be held to extreme accuracy of frequency stability. Temperature compensation may be applied to crystal oscillators to improve thermal stability of the crystal oscillators. The crystal size and cut determine the values of L, C, R, and C dash. The resistance R is the fraction of the vibrating crystal. Capacitance C is the compliance, and inductance L is the equivalent mass. The capacitance C dash is the electrostatic capacitance between the mounted pair of electrode with the crystal as the dielectric. So This is the circuit diagram of the crystal oscillators, in which we have a crystal at the output side circuit or across the capacitor C1 and C2. Crystal is the quartz crystal. So here diagram A is the symbol of vibrating piezoelectric crystal, in which three components, passive components L, R, and C connected in series, and one capacitor is connected parallel with it. So here mounting electrodes, and the second one is equivalent electrical circuit of the crystal oscillators, in which inductance, reactance, and capacitance reactance also. And the circuit second or B has two resonant frequencies. At this series resonant frequency Fs, the reactance of the series LC are 0, that is omega S L equal to 1 upon omega S C. So omega S equal to 1 upon under root LC. And B omega P is the parallel resonant frequency of the crystal of the circuit greater than omega S, where omega P L minus 1 upon omega P C equal to 1 upon omega P C dash. So we have omega P square equal to 1 upon 2 into 1 upon C plus 1 upon C dash. So omega P equal to under root 1 upon 2 into 1 upon C into 1 upon C dash. So therefore omega P and omega C are shown in this figure second B. At the parallel resonant frequency, the impedance offered by the crystal to the internal circuit is very high. The resonant frequency of a crystal vary inversely as the thickness of the cut. So F equal to 1 upon T. So what is the applications of oscillators? So there are some applications of oscillators. So oscillators are a common element of almost all electronic circuits. They are used in various applications, and their use makes it possible for circuits and subsystems to perform numerous useful functions. In oscillator circuits, oscillation usually build up from zero when power is first applied under linear circuit operation. The oscillator's amplitude is kept from building up by limiting the amplifier saturation and various non-linear effects. So oscillator design and simulation is a complicated process. It is also extremely important and crucial to design a good and stable oscillators. So oscillators are commonly used in communication circuits. All the communication circuits of different modulation technique, AM, FM, PM, the use of an oscillator is must. So oscillators are used as stable frequency source in a variety of electronic applications. Oscillator circuits are used in computer peripherals, counters, timers, calculators, phase lock loops, PLL, digital multimeters, CRO, and numerous other applications. So oscillators convert DC to AC. Oscillator has no input signals, and oscillator behavior is opposite to that of rectifiers. The conditions and frequencies of oscillations are classified as, so type of oscillators given here and conditions for oscillation and also frequency of oscillation. So first type of oscillator is that Hartlay oscillator. Condition for this oscillation, HR equal to omega L1 upon omega L2 plus RHI omega square L1 L2. So frequency of this oscillation equal to F equal to 1 upon 2 pi under root LC. Second one is the Colpitt's oscillator. So condition for this oscillator of oscillations, HR equal to C2 upon C1 plus RHI minus omega square C1 C2. So frequency of this Colpitt's oscillator is F equal to 1 upon 2 pi into H O E upon H Fe C1 C2 plus 1 upon LC1 plus 1 upon LC2 under root. Next oscillator is phase shift oscillator. So condition for this oscillator of oscillations, the transistor should have an HRE of 56 when RL equal to R, and frequency of phase shift oscillator is F equal to 1 upon 2 pi under root 10 into CR. And next one oscillator is Wien bridge oscillator. So condition for oscillation of this oscillator is R1 upon R2 equal to 2. So frequency of this oscillator is F equal to 1 upon 2 pi RC. And last one is the crystal oscillator. So there is no condition for oscillation of this type of crystal oscillator. So crystal oscillator frequency F equal to 1 upon 2 pi under root C upon C plus C dash upon LC into C dash. So these are the some points to remember for the oscillators. So these are the reference books for this topic, electronics device and circuit by Millman and Algas. Now we have some multi-choice questions, and we will discuss these multiple questions one by one. So first questions, an oscillator convert option A power into DC power, power second into AC power, and third one mechanical power into AC power, and D is the none of the above. So correct answer is option D, convert power into AC power, DC power into AC power. In question second, in an LC transistor oscillators, the active device is first LC tank circuit, second biasing circuit, third transistor, and fourth none of the above. So correct answer is option third. In LC transistor oscillator, the active device is transistor. In questions third, in LC circuit, when the capacitor is maximum, the inductor energy is option first minimum, option second maximum, option third may have halfway between maximum and minimum, and option fourth none of above. So correct answer of option A, that is minimum. And next, in an LC oscillator, the frequency oscillator is L or C. Option A, proportional to square of. Option C, directly proportional. Option third, independent of the values. And option four, inversely proportional to square root. So correct answer is option 4. In an LC oscillator, the frequency of oscillator is inversely proportional to square of L or C. Next questions, an oscillator produce option A, damped, option B, undamped, option C, modulated, option D, none of the above. So correct answer option D, undamped. An oscillator produce undamped oscillations. And next questions, an oscillator employ positive feedback, negative feedback, neither positive or negative, data insufficient. So option A is correct, and oscillator employ positive feedback. Thank you very much.